So before I start from where I stopped last time, I'll do a very quick recap as I always do. I told you where exactly this catalytic reformer fits in terms of the entire refinery, and essentially it actually takes the heavy naphtha and after hydrotreating to remove sulfur and nitrogen, we put it into this machine called catalytic reforming. And basically, the purpose of a catalytic reforming is to make either gasoline or BTX. So we actually went through the whole history of catalytic reforming as well as the history of gasoline because and the vehicles because all these three go hand to hand. The more impurities in gasoline, the more carcinogenic material in gasoline, the more is the environmental impact. And whatever the vehicles need in terms of octane, we have to do something to actually provide that octane. And over a period of time, the whole world went from leaded gasoline to unleaded gasoline, including our own country. And so actually, how do we improve the octane? So we had to actually, implement catalytic reforming units in all refineries to be able to. But the moment you put catalytic reforming unit, the benzene level goes up. So actually, initially, when the country went to completely ULG means unleaded gasoline. So when the country went all the way to complete unleaded gasoline, we still had relaxed benzene levels in the gasoline. But then this was also tightened up as we went along. And today, the petrol that you buy in the petrol station has less than 1% benzene. It has less than 35% aromatics and it has less than 21% olefins. So it is actually quite kind of a reformulated gasoline in order to actually not only meet the requirements of the vehicle in terms of anti-knocking properties and to be able to provide the octane for you to travel at 120, 160 kilometers an hour, but also to actually save the environment. Okay. So that the environmental impact is minimized. And I actually told you how it actually compares. In fact, BS6, where we are today, which is equivalent to Euro 6. So actually, you will be very proud to know that although we had a lot of catching up to do with the rest of the world in terms of our fuel properties, but we did it in a very, very fast way. And 2020, 1st April 2020, the entire country went to Euro 6 equivalent, and the Western world, some of the Western nations, including China, etc. I mean, China is not a developed country, but even many countries have not actually they have not reached to the level that we have reached in terms of the gasoline and diesel properties. So I talked to you about catalytic reforming. It is just a transformation of a molecule from one hydrocarbon type to another hydrocarbon type. Essentially, it converts paraffins and naphthalene to aromatics. And we talked about various streams which go into the gasoline pool, like isomerate, FCC gasoline, etc. And what does a reformate what role does a reformate play there? In addition to gasoline, reforming is also used to make aromatics, and this is how we actually in Reliance use catalytic reformers. We don't produce gasoline. Gasoline is a byproduct, if at all it is produced from our catalytic reformers. Basically, the idea is to actually make aromatics. And since you are converting a higher hydrogen content hydrocarbon to a lower hydrogen content hydrocarbon like paraffin or naphthalene to aromatics, you're bound to produce hydrogen, which is a very important resource in the refinery, particularly when you want to do hydrotreating to remove sulfur. And we went through the entire range of octane numbers for various molecules. Also talked about why it is very important to have naphthenes, and any feed which is rich in naphthenes is an ideal feedstock for catalytic reforming, and we'll learn later on why. And I also taught you that if suppose somebody throws up a feed composition, a naphtha composition to you, if suppose the naphtha composition, talks about almost negligible naphthenes, high aromatics, and a higher isoparaffin to normal paraffin ratio around 3, you can be rest assured that this must be reformate without the other guy telling you. And we went through the history of catalytic reforming. In fact, the history of catalytic reforming is same as the history of vehicle development in our in the entire world. They went hand to hand, kind of made for each other. And any development in the vehicle engine required a different fuel, and catalytic reforming is one of those technologies which actually met that requirement. And then when we came to the chemistry and catalysis, I just gave you a short recap about the thermodynamics, basically chemical thermodynamics, and differentiated between reactions in which you have a limiting component, but the reaction goes to 100% conversion, which is what we call as a spontaneous reaction, where the free energy change is highly negative, and reactions which are equilibrium controlled, where the reactants can also go back to the products like ammonia production. And you talked about the role of the catalyst, and you already know what the catalyst does. It actually reduces the activation energy required to actually to make the reaction go through from the reactants to the products. And this cartoon actually explains really, I mean, how you drill a tunnel through a mountain and make it easy for you to go to the other side. And Catalyst actually does that. And then actually we came to the structure of this catalyst, and this particular slide is extremely important for you to understand that any heterogeneous catalyst, and I underline this word, any heterogeneous catalyst has to have a functionality, okay? And it has to have, sites where actually the reactions can happen. Now, typically, catalytic reforming catalyst has two sites. So one is actually the metal site, and the other is the acidic site. And so these are actually provided by platinum, and the acidic site is provided by chlorinated alumina. And this is just aluminum oxide, Al2O3, but it is highly pure aluminum oxide. It is gamma aluminum, which is actually impregnated with the chlorine in order to make it acidic, so that we have an acidic function for us to actually do the reactions that we are looking for. So that actually brings us where we stopped last time in terms of what kind of reactions really happen in catalytic reforming. Okay. So there are two types of reactions which happen, and this is typical for any reactor. You have a desirable reactions and you have undesirable reactions. So the desirable reactions, which we will actually go through in greater depth now, they actually all put together lead to a higher octane number of the products, and for producing high purity hydrogen. And these are the reactions which we like to promote or support so that we make more money. On the other hand, nothing, in an actual world, if you have something positive, there's always something negative as well. And so we do have some undesirable reactions which we try to minimize. Okay. And this is basically leads to, if you don't minimize that, it leads to reduction in octane number, loss of products, or actually having an impure hydrogen. So let's see which are the desirable reactions. There are all the reactions that happen, and there are many reactions that happen in catalytic reforming depending upon the feed composition. But all these reactions can be actually, categorized or bracketed in three categories. The first is, and the most important, and one of the most spontaneous reactions that happen, or I would say not spontaneous, but fast reaction that happens in catalytic reforming is actually dehydrogenation of naphthenes to aromatics. It's relatively straightforward. Okay. Then second is, of course, paraffins. So we have to go through, cyclization and then dehydrocyclization. So basically, it is converting paraffins to naphthenes and then naphthenes to aromatics. So that is the third. That is the second reaction. And the third, of course, is isomerization of paraffins and naphthenes. So paraffins means a normal paraffins going to isoparaffins, and when you talk about isomerization of naphthenes, it is actually cyclopentanes going to cyclohexane. So just remember that these are the three desirable reactions in catalytic reforming. The first one, as I said, is dehydrogenation of naphthenes to aromatics. And I'm giving here an example. For example, if suppose you have a cyclohexane, this of course has an alkyl group, but any naphthene, but it has to be a six-membered ring. Okay, cyclopentane will not work here. So if you have a naphthene like a C6H12, which is cyclohexane, that gets dearomatized immediately to make benzene. So if you have cyclohexane, it will go to benzene. If you have methyl cyclohexane, it will go to toluene. And it's an equilibrium control reaction, but of course, for every mole of cyclohexane, you produce 1 mole of benzene and 3 moles of hydrogen. And you can understand this extremely quickly. And this is, of course, a highly endothermic reaction. It's highly endothermic reaction, and that's why we have to provide a lot of heat to the feed. We have to preheat the feed to almost like 450, 500, or even, I mean, not 450, even more than 500 degrees Celsius, sometimes even 520, 540 degrees Celsius, to be able to provide that heat required for dehydrogenation reaction. And actually, this reaction, if you see, 1 mole actually ultimately ends up into 4 moles. So 1 mole of cyclohexane gives 1 mole of benzene plus 3 moles of hydrogen. So if you apply, and if you still remember the Le Chatelier's principle, which you studied in chemistry, so whenever there is an expansion in volume, like here, 1 mole of naphthene going to 4 moles of product, actually this reaction will get helped in terms of forward reaction if you drop the pressure. So this reaction, so generally, catalytic reforming reactions, the desirable reactions actually, you get a higher yield of aromatics if you decrease the pressure. Similarly, since it's an endothermic reaction, according to Le Chatelier's principle, if you actually, do the reaction at a higher temperature, you will get a better yield from left to right, like naphthenes to aromatics. In other words, it suppresses converting aromatics back to naphthenes because aromatics can get saturated actually to naphthenes. But this is, of course, exothermic reaction, aromatics getting saturated with hydrogen. So idea is that if you increase the temperature to that extent, it will suppress the backward reaction. So just remember, hydrogenation of cyclohexane to benzene is, it is higher if you actually do this reaction at a higher temperature and a lower pressure. And this particular reaction, since it's a dehydrogenation reaction, it is actually supported by the platinum of the catalyst. So when you talk about the two sites, the platinum site is the center for dehydrogenation or hydrogenation. So any hydrogen transfer happens because of the metal site on the catalyst, and any transformation of the molecule in terms of cyclization of paraffins or isomerization of paraffins or naphthenes happens because of the acidic sites on the support. So this is actually a reaction which is enabled by the platinum on the catalyst. The second is the dehydrocyclization of paraffins, so the second bucket of reactions. And here is an example where I've shown a heptane molecule. Any paraffin lower than C6, I repeat, any paraffin lower than C6 will not actually transform, okay? Because actually the minimum number of carbon numbers that you need to make aromatics uh, is actually 6. Minimum number of carbon atoms required is 6. For example, if I'm talking about normal pentane, etc., they will actually just go through or maybe crack, and they will not get transformed. But if suppose you have hexane or heptane, what will happen is that actually because of the metal site on the catalyst, a dehydrogenation reaction takes place, and you get an olefin that is C7H14. So this is like heptane getting converted to heptene, and the acidic sites on the catalyst then actually cyclize this to make methyl cyclohexane. And that actually then, so this is the acidic site. So this reaction is happening because of the acidic site. And then this reaction, dehydrogenation again of methyl cyclohexane to toluene, happens because of the metal sites. So actually, you can see that it's a three-step process, multiple steps. Okay, so say paraffin going to an olefin, and then olefin getting converted to a corresponding naphthene, and then naphthene getting converted to aromatic. So if suppose I have hexane here, it will convert to one hexene, and then one hexene will go to cyclohexane, and then cyclohexane to benzene. So this is a pretty slow process actually. Because there are three steps involved. Most desirable because if suppose you got a paraffinic feedstock, we would like to actually convert that to aromatics. Of course, the catalyst will actually convert the normal paraffins to isoparaffins as well. But then, based on the table, you would have seen that isoparaffins have high octane number, but not as high as aromatics. Okay. Again, because the number of moles are high, from one mole you end up actually making 4 moles. You still have, the same application of Le Chatelier's principle. That means it is favored at a lower pressure and a higher temperature. And minimum six carbon chain, as I told you, is necessary. These reactions, C5 paraffins will not actually participate in this reaction. Neither will be cyclopentane. And if you look at the thermodynamics of this reaction, the larger the paraffin, that means CH, C9, C10, the faster is the reaction. Okay, and the reaction, of course, as we've seen, is promoted both by the metal function as well as the acidic function. The third category of reactions is actually the isomerization of normal paraffins. And the metal site on the catalyst has no role to play here. This is essentially promoted by the acidic sites. Very mildly exothermic reaction, but it is reasonably fast at those temperatures. And thermodynamically, it is dependent on temperature. But since we have one molecule going to one molecule, it's only branching of normal paraffins to an isoparaffin. There is no increase in the number of moles or reduction in the number of moles. So pressure has relatively no impact here. And this reaction is kinetically favored by high temperature, but actually it is not favored thermodynamically. Thermodynamically, isomerization reactions are favored more at a lower temperature, but it is favored at a because of the Arrhenius equation. The rate of reaction is high to reach. So basically, at high temperature, the equilibrium composition is low in converting normal paraffin to isoparaffin. But then we have to have a trade-off between how much we can go and how fast we can go. Right. This is a kind of and we need a certain temperature in catalytic reforming because we need to make these two reactions happen, and these two reactions are favored at a higher temperature. So again, the temperatures is like a trade-off between what exactly we are looking for. So and then the second isomerization reaction, which is equally important equally important to normal paraffin isomerization, is the isomerization of cyclopentanes. So cyclopentane is a 5-membered ring structure. It cannot convert to aromatics directly by dehydrogenation. So the catalyst actually the acid site on the catalyst, it actually converts a cyclopentane. Now in this case, this is methyl cyclopentane. Sorry, this is ethyl cyclopentane, and this gets converted to something like methyl cyclohexane. Which is a tough reaction. It's a desirable reaction because once you actually make a naphthene, it will immediately convert to aromatics. The difficulty is the problem of the ring rearrangement, and the chances are that when you are actually opening up this ring, it might actually open up into a normal paraffin. And in that case, then, it might be difficult then to convert. And I mean, we are actually increasing the degree of difficulty. So the idea is that any feed that we have going into the reformer, if we have less cyclopentanes and more cyclohexanes, it will be good. So what we are trying to do here is to differentiate between the type of naphthenes we are having in the feed. And as a refiner, we actually ask for that information when we are trying to look at the suitability of that feed in our unit. So it's not just the naphthene content which we are happy with. We are also looking for what is the distribution of those naphthenes in terms of cyclopentanes and cyclohexanes. If it is higher cyclohexanes, that is good news as compared to having more cyclopentanes. Okay, although the naphthenes might be higher. So this is actually a summary of all the desirable reactions that we talked about. The dehydrogenation reaction we talked about, like alkyl benzene going to, alkyl naphthene going to an alkyl benzene. And this tells you about the heat of reaction. You can see that it's highly endothermic reaction. And similarly, the iso normal or isoparaffin getting isomerized, getting converted to naphthene. On the other hand, you have isomerized, and then once you convert to naphthene by the hydro decyclization, then you actually convert back from naphthene to aromatics. Similarly, isomerization, dehydrogenation, this is actually a cyclopentane ring getting converted to cyclohexane and ultimately going to aromatics. And we discussed all of that, including this reaction, which is the hydrodecyclization of paraffin. This is the thermodynamic data in terms of heats of reaction. This you can see is highly endothermic. And cyclohexane to benzene, methyl cyclohexane to toluene, methyl cyclopentane to cyclohexane. This is the isomerization of a cyclopentane to cyclohexane, mildly exothermic. Then normal hexane to 2-methylpentane. This is actually isomerization reaction. This is dehydrocyclization of a paraffin to aromatics, highly endothermic reaction, etc. Now coming on to the undesirable reactions, which we call adverse reactions in catalytic reforming. And ultimately, the operating conditions in the catalytic reforming, including the design of the catalyst, is actually done in order to balance between the desirable and the undesirable reactions. So the adverse reactions are hydrocracking, because at those temperatures and in the presence of hydrogen, hydrocracking will kick in, and hydrogenolysis. And I'll talk about what do these these two terms mean. The hydrodealkylation of aromatics, because once you actually make toluene, it can convert back to benzene, and so on and so forth. And coking, that is the carbon deposit. If you recall, I told you that anything above 360, any hydrocarbon will actually decompose, and when it decomposes, it will make carbon. So by putting a large quantity of hydrogen. So when we put the feed in the catalytic reformer, we put it along with the hydrogen, so that at that temperature we don't we deaccelerate the decomposition of the hydrocarbons to make coke. So let us go through each one of them. If you look at the hydrocracking reactions, as the name suggests, basically it is breaking the larger molecule to the smaller molecule. And when you do that, when you break the larger molecule, any larger molecule, whether it is paraffin, naphthene, or aromatics, in this case, you can see that a paraffin gets converted to an olefin, and then hydrogen is produced because of hydrocracking. And then the acidic function actually then crack this further to make propane and butene. And then butene, since the whole system is with hydrogen atmosphere, the metal function will then actually convert it to normal butane. So ultimately, what is happening is that something like 1, 2, 3, 4, 5, 6, 7. So we got normal heptane getting cracked to normal butane and propane, and that's why actually we actually get. I won't say a very large quantity, but yes, we do get some quantity of LPG, LPG components like C3C4 as one of the byproducts from catalytic reforming, because at 520, 540 degrees Celsius, and with the hydrogen atmosphere, this reaction is bound to happen, because not only you got platinum, that is the metal function to do the dehydrogenation step to make an olefin, and then once you make olefin, You have a double bond here, which can crack at that end, and you get propane and normal butane. So this reaction is favored by three things: the high temperature, the pressure, as well as actually, if in fact, if you try to operate at a lower pressure, this actually, because 1 mole is going to 2 moles, it actually is favored by a lower pressure. Similarly, the hydrogenolysis. What is hydrogenolysis? Is that you have one, two, three, four, five. So you got now normal heptane, and along with hydrogen and the platinum on the catalyst, it actually breaks up this normal pentane to hexane plus methane. Okay, and so this is called hydrogenolysis, where this molecule will come and sit on the catalyst site. And since there is hydrogen, the catalyst site actually helps to crack this material and make methane plus hexane. And you could have further hydrogen addition to make even ethane and pentane and so on and so forth. This is a highly exothermic reaction because you have a hydrogen addition. Always remember, in our hydrocarbon industry, whenever you are actually hydrogenating something, whenever there is an addition of hydrogen, that reaction is always exothermic. And when you are taking away the hydrogen, it is endothermic. So catalytic reforming overall is an endothermic reaction because we are removing hydrogen from cyclohexane and paraffin to make them aromatics. So this actually also helps to increase the LPG production. Actually, that's why you get LPG. Of course, we don't run reformers to make LPG. We have LPG being produced by other process units like FCC unit or cokers, etc., etc. I mean, reformers are not run to produce LPG. Okay, we run it to make more liquid yields. And the second bucket of reactions which are undesirable in catalytic reforming is where actually it's a removal of the alkyl group of an aromatic ring. So if you have, let's say, a metaxylene with hydrogen, actually you can it gets converted to toluene, plus you get methane. So this is actually like fuel gas that you produce. It does consume hydrogen and produce methane, favored at high temperature and high pressure, promoted by a metallic function of the catalyst because there is a hydrogen addition. And since there is a hydrogen addition, these reactions are exothermic. So what we try to do is try to maintain an optimum combination of pressure and temperature so that this xylenes are important actually. I mean, production of xylene is very important in catalytic reforming. And say orthometa paraxylene, out of which actually the paraxylene is extremely important because the paraxylene is the precursor, is the starting raw material to make terephthalic acid, purified terephthalic acid, and then the terephthalic acid is used to make polyester fibers. So whether it is the PET bottles from which you drink water, so that is the polyethylene terephthalate. So what do we do in our petrochemical complexes is that we oxidize the paraxylene to make terephthalic acid, and then we actually do esterification of terephthalic acid with monoethylene glycol to make the monomer, and that is actually then polymerized to make the polymer, which is called polyester. Okay, so the clothes that we wear, and there are many things that we use actually has polyester fiber in it, and also actually it is polyethylene terephthalate, so that is also used to make bottles. Or to use to fill up Coke or other lemonades that you and I drink. The other adverse reaction, the third kinds of adverse reaction is the coking, which is because of the decomposition of the feed. But as I told you, we actually do this reaction under very rich hydrogen atmosphere, which actually suppresses the coking reaction. But nonetheless, some heavier aromatics like polynuclear aromatics do come along with the feed, as well as actually the olefins do get produced within the in the reaction, both by hydrocracking as well as by hydrodecyclation of paraffin. So these olefins actually tend to polymerize and then tend to make coke. So it's a very complicated chain of reactions by which coke is formed, but nonetheless, coke is formed. And actually, the lower the operating pressure of the reformer, the more coke gets formed. The reason is that we want to operate it as low as possible because we are favoring the dehydrogenation of naphthalene to aromatics as well as dehydrocyclization of paraffins to naphthenes. So the isomerations, they don't get affected really. But on the other hand, if I go down on pressure, then some of these undesirable reactions, like, for example, hydrocracking happens, hydrogenolysis happens. So, and actually the coke deposit also happens. I mean, because of low pressure, there's a more of cracking of the hydrocarbons, which actually leads to coke deposit. So, when actually the catalytic reforming was invented by Vladimir Hensel way back in 1942, and the first commercial unit went on stream in 1949. It actually operated at pretty high pressure just to actually make sure that the catalyst doesn't get deactivated very quickly. Because the faster the coke deposit, the faster is the deactivation of the catalyst. So those units were operated at 70 bar. And then slowly and steadily, as more and more inventions took place, like going from platinum catalyst to a bimetallic catalyst, and I'll talk about the catalyst in a moment, in a few minutes. Actually, the pressure kept on coming down, and today, and then the technology changed from semi-regenerative reforming to continuous catalytic reforming, and where actually we regenerate the catalyst continuously in another vessel. So basically, the catalyst exits from one reactor physically. It exits and goes into another reactor where actually we regenerate the catalyst, and we actually return the catalyst back to the reactor. So that actually helps us to operate the reaction at a much lower pressure. So modern CCRs, any catalytic reforming unit built today will operate at as low as 3.5 kg. So we have actually improved upon this technology very significantly. In 1949, operating at 70 bar to today at 3.5, and actually it has helped in terms of the desirable reactions. So this is a summary of the undesirable reactions, and we have gone through all that. I thought this is just for you to do a complete one single snapshot of all the reactions that happen. So this is the summary of the thermodynamics and the kinetics comparison of the various reactions, both desirable and undesirable. Like for example, the cyclohexane dehydrogenation is the first reaction that ever happens in the catalytic reforming, highly endothermic, and it reaches equilibrium pretty quickly at that temperature and pressure. So if you reduce pressure, it helps, but if you increase pressure, it has a negative impact. Increased temperature it produces, and of course, this reaction produces hydrogen. Similarly, cyclopentane dehydroisomerization, that is converting to from cyclopentane to cyclohexane and then to aromatics. The aromatics part is quick, but the cyclopentane to cyclohexane can be slow. Overall, it's endothermic because of the cyclohexane going to aromatics. This also reaches equilibrium, and the impact is roughly the same. Same thing with the paraffin isomerization. This, of course, is slightly exothermic. This is also pretty rapid reaction because it is felicitated by the acid sites, and it's the same thing in terms of pressure, temperature. Well, actually, the pressure doesn't really have much impact here. Paraffin dehydrocyclization. This is actually the first step before cyclohexane dehydrogenation. So same thing, but of course, as compared to the first reaction, this is rather slow because there are three steps involved, and this doesn't reach equilibrium at all. I mean, we don't have time in the reactor for this to reach equilibrium. So some paraffins do exit without getting conversion, and that's why when you saw the reformed composition, you saw some paraffins also there. although the isoparaffin to paraffin ratio was 3. And of course, hydrocracking, it is we actually slowed this reaction down, by operating the whole thing at with a very high hydrogen to hydrocarbon ratio. It's exothermic, of course. So higher pressure and higher temperature actually felicitates hydrocracking, which we don't know, but it's a major consumer of hydrogen. Nonetheless, it is evitable, so we can't help not doing any hydrocracking at all. But this graph, this was just a qualitative discussion. This is more quantitative in terms of, I think, the temperature profile. So this is temperature. I think it has got hidden away. On the 510, um, yeah. So you can see from here 510 and 450, and on the y-axis is log k. So this is more like a Arrhenius plot, if you can say that. And these are the Arrhenius, activation of activation energy as you go from dehydrogenation to hydrogenation to isomerization, the cracking, dehydrocyclization, and then coking. So you can see that any coking reaction is actually suppressed if you go down on temperature, but generally the reformers operate at a temperature above 510 because the dehydrogenation reaction is much higher at higher temperatures. So we want to actually complete the dehydrogenation reaction up to the equilibrium. The hydrogenation is actually not much impacted. We don't have much of hydrogenation anyway. Isomerization is also favored at higher temperature, so because of the rate of reaction and the other reactions that we discussed. Um, if you look at the effect of reactor pressure, so these are the two important variables: the reaction temperature and reaction pressure. So if you plot the partial pressure of hydrogen on the x-axis versus the rate of dehydrogenation, log of rate of dehydrogenation, if where rate of dehydrogenation is taken as a basis of 100, so 2 is representing the rate of dehydrogenation as a base. So this is just to compare the other rates of reaction and the impact of pressure vis-a-vis the dehydrogenation, that is cyclohexane to aromatics. So you can see that the two lines in the two dotted lines actually are the ones which we don't really want. Higher pressures actually do actually reduce coking, but and lower pressures increase coking, but the cracking is the other way around. Cracking is favored at a higher pressure. So our units actually operate in this region. Okay, and in this region, if you compare with two, basically you do have less of coking in those at those pressures, but sorry, we have very high coking, of course, at lower pressure, but the cracking is lower. So this actually tells you the impact of pressure. And we'll talk about more of that when we talk about how we optimize temperature and pressure in operating units. And these graphs are then very important in terms of effect of various reactions, effect of temperature on various reactions, and effect of pressure on various reactions. These graphs we will recall when we talk about the effect of operating conditions on the yields, etc. When we talk about the technology. Now, coming on to the heart of this unit, which is the catalyst. Okay, and we have had a large number of discussions already on the catalyst, and I told you that catalyst is platinum catalyst, which is actually supported on the acidic alumina, or what we call as a chlorinated alumina, which is highly pure alumina. The metal is very finely dispersed. Actually, platinum is expensive, as you know. It is even the price is even higher than gold. But so we have to, so we can't actually put lumps of platinum here. The technology has evolved to the extent that the catalyst particles are actually in a nano form. In fact, right from the beginning, if you ask me, the metal, the platinum was always finely dispersed on the catalyst surface. And scientists developed methods by how to do that. Just to give you an idea, like so all of you may not have actually, you know, developed a catalyst on your own. But how these things are done is, I'm not an expert on catalyst myself. Actually, this is more in the expertise of inorganic chemists. Actually, people who are inorganic chemists, and they actually have the kind of skills, and these are very specialized skills. Actually, it is not trivial to make a catalyst. Let me tell you. These catalysts, are very expensive. Just to give you the number, if you forget about the platinum part on this catalyst will cost you something like 4,000 rupees a kilo without the platinum. And the platinum part is actually, priced as per London Metal Exchange. So when the catalyst manufacturer sells you this catalyst, they actually sell you, they quote in two different ways. They actually give you a quotation for the catalyst as such without the platinum. And then they will tell you how much platinum would be there on that catalyst in terms of tons of, of platinum. And that will be priced separately. So actually, in India, we link up with Hindustan Platinum Limited. There is a company called HPL, Hindustan Platinum Limited. So all the platinum sourcing that any refinery or petrochemical plant does is through Hindustan Platinum Limited. So we actually, although the catalyst manufacturer himself will put platinum on it, but the money exchange with the catalyst manufacturer happens through this company. And that is actually the prices are governed like the way the stock exchanges are governed, because as you know, the precious metal prices change every day. Okay, and it's a traded commodity. So both so silver, gold, platinum prices change daily. So depending upon what day of quotation it is, the platinum price is picked up from the price in the London Metal Exchange. So basically, this catalyst is so finely dispersed, even in good old days. But now, with the invention of machines like tunneling electron microscope, where you can actually see almost at atomic level, now people have discovered that actually this was nano catalyst. Now, of course, it is extremely fashionable to talk about nano, whether it's a nanoparticle or a nano catalyst or a nano fiber or a nano carbon tube, etc., etc. But actually, if you ask me, this platinum is actually present in a nano form. The particle size is actually at the level of nano meters on the catalyst surface, and that's why actually it provides very large surface area for the reactions to happen. In late 60s, actually, the scientists discovered that just pure platinum may not be is not really good enough. We need to actually add another metal, which actually helps the dehydrogenation and the hydrogenation function of the catalyst, and it actually suppresses the coke formation. And after a lot of research, people came up with metals such as tin. I think that particular list is here. Yeah. So they came up with metals like iridium, rhenium, tin, etc. So there were a large number of metals which were tried in combination with platinum. Platinum is the king. We need platinum, all right. But if you actually put another metal along with the platinum, it actually helps the hydrogenation function, as well as actually the major function of a of a second metal is to actually suppress coking. And so in late 60s onwards, the reforming catalyst is no longer pure platinum worldwide. It is actually along with another metal. So it is now called as a bimetallic catalyst, which consists of platinum plus another metal, which is actually a promoter, like rhenium or tin or iridium, etc. But over a period of time, two metals ultimately kind of stabilized in terms of their usage worldwide. And I'll come back to that in a moment. But let me tell you, I mean, this is rhenium and tin. Okay, so rhenium is one metal and tin is another metal, which is actually used in combination with platinum to make the bimetallic catalyst. Why actually we do that? The main features of this catalyst, of course, is the high purity gamma alumina support. So you get high mechanical resistance. So your attrition is high, attrition is low, and you have a more mechanical strength, so that the catalyst doesn't get crushed inside the reactor. And the platinum, if it is associated with rhenium, which is actually gives you very high stability and selectivity. That means it actually promotes production of aromatics while suppressing. So high selectivity means it actually reduces the undesirable reactions that we talked about. And the platinum with tin is actually again provides you high selectivity. Plus, actually, this bimetallic catalyst helps you to actually burn off the coke easy. So it acts as a catalyst for you to burn off the coke easier when in the regeneration step. So the combination of all these qualities provides us pretty high reformate yield. In other words, less of byproducts like methane or LPG. Once you get, if you get very high reformate yield, by default you will get high hydrogen because reformate is produced by dehydrogenation reaction, and high on-stream factor because you have less coking. And overall, actually, you can end up putting less catalyst because this catalyst is much more active as compared to just pure platinum. So the stability is improved, and the hydrogenolysis action of platinum, if you recall, the hydrogenolysis was actually where heptane reacts with hydrogen to make propane, butane, etc. So that is actually suppressed by this promoter or the second metal, and the acidity of the chlorinated gamma alumina is tuned to with respect to these promoters. So as I said, it reduces the dry gas, the C1, C2, and the LPG production. In other words, it improves the selectivity as we talked about here. So how much do we add? Actually, we add something like 50-50%. So basically, the amount of if you take this catalyst, it will contain something like 0.3% by weight platinum. I repeat, any reforming catalyst would actually contain roughly about 0.3%, 0.3% by weight platinum, and around the same percentage the other metal like rhenium or tin. So over a period of time, worldwide, there are two types of technologies which are used in catalytic reforming. One is called the semi-regenerative reformers, and the other is called the CCR, continuous catalyst regeneration. Based because of the typical property of rhenium, platinum rhenium catalyst, the bimetallic platinum rhenium catalyst is most commonly used in the semi-regenerative reformers, and we will talk about in greater detail about these two different types of technologies: the semi-regenerative reforming and what is called as a moving bed or CCR reformers. And platinum tin is used in the moving bed reactors. Or at least what we call as continuous catalyst regenerator. So two types of technologies. people use. In fact, in India also we have both these technologies operating, semi-regenerative reformers as well as CCR. But in semi-regenerative reformers, you use platinum rhenium, 0.3% platinum, 0.3% rhenium. And in CCR reformers, we use 0.3% platinum and 0.3% tin. When the two metals are equal, this is called as a balanced catalyst. It is called balanced catalyst because each of these metals are equal, 0.3% platinum, 0.3% rhenium, or 0.3% platinum or and 0.3% tin. But over a period of time, people also discovered that if you put more of the second metal, like for example 0.6% rhenium or 0.6% tin, then actually the coke deposit reduces significantly. So this is actually called skewed catalyst, SKEWED. It is called skewed catalyst, where the rhenium content is higher than the platinum. So this is also unbalanced, but it actually helps you. How actually physically it helps you is that suppose you got two platinum particles, and there's a rhenium sitting in between or tin sitting in between. It helps you to break that carbon bridge that can get formed between two platinum particles. So it actually breaks that, and it helps you to actually reduce the coking. And the more number of rhenium particles you put, the less is the coking, and vice versa. So this is called as a skewed catalyst. More rhenium and less platinum. Similarly, you have the acidic function of the catalyst, where actually it is aluminum oxide with it's a chlorinated alumina, as I said. So this is the aluminum structure, aluminum oxide structure with the chlorine attached to it. Around about 1 to 2% by weight chlorine is present in this catalyst base, and this is an optimum level in order to provide the kind of acidity or acid function that we need to promote the cyclization and the isomerization reactions. So there is actually this ratio is a function of the water and the HCl content. So in reformers actually, this chlorine keeps on leaching out actually as the reaction happens. So we have to continuously add a kind of a chemical which brings in chlorine along with it. Something like carbon tetrachloride or chloroform and things like that. So chlorine containing hydrocarbon is added to maintain the acidity of this catalyst. It is actually so. This is just to get deeper into it. As I said, chlorine level on the catalyst must be adjusted to between zero point 0.9 to 1.1% by weight, and it actually continuously leaches out. The moisture, if it is present in the feed, that actually results into removal of chlorine. So actually, it will be replaced by the OH group. Okay. So if you look at if this is my chlorinated alumina, and if there is moisture coming along with the feed, then actually the moisture will replace the chlorine, and you get HCl formed, and you ultimately get aluminium hydroxide. Which actually reduces the activity of the catalyst because there are no acid sites left anymore. So this is of course the simplified representation of the catalyst support, and we try to actually optimize the balance between OH and Cl in order to actually make sure that we have the desired amount of acidity. And also the moisture in the feed is minimized. I mean, it's almost bone dry feed actually, so that we don't actually reduce the chlorine present on the catalyst. But if so, nonetheless, as the reaction continues, the chlorine leaches out, and so we actually keep on replacing that chlorine by adding a chlorine containing hydrocarbon. So this is what I had said so far. The metals are platinum with promoter like rhenium and tin. Iridium and germanium are no longer actually used, but of course, there are several patents which actually talk about the advantage of putting iridium and germanium. The metals, as I said, platinum can vary from 0.23 to 0.38. Roughly 0.3% is what you will find on the catalyst. And here in Reliance, the analytical, what I mean, when you have the catalyst, when you have the spent catalyst, these catalysts go for 5 years. Okay, they don't actually, degenerate that quickly. So they're pretty sturdy. They go for 5 years. And after 5 years, of course, because of sintering and all kinds of things, the catalyst get deactivated quite a bit. And, that's the end of life of that catalyst. So you have to replace that catalyst with the fresh catalyst. And so what do we do with that platinum then? Okay, because there are several tons of catalyst sitting on that catalyst, several tons of platinum sitting in that catalyst. So what we do is that this spent catalyst is analyzed several times to establish the platinum level, and then based on that, this catalyst is sold to platinum recyclers, which actually recover the platinum from there, and they pay you the money. So it's like a Randiwala type who's actually paying you the money for the platinum. The base material is useless for them. And they also recover the rhenium, which is zero point 0.3 to zero point 0.6. If it is zero point 0.6, it is called skewed catalyst. And similarly, the 10.3%, if it is zero point 0.5, it is called skewed catalyst. And there's a huge, very high dispersion of the catalyst. In fact, this research still continues. Okay, as we keep on going, there are new generations of reforming catalysts which are being brought into the market. And the chloride content, as I said, is 1 to 1.2%. This actually slide is a very important slide, which actually tells you the role of these two sites, which we talked about. It's a good summary of what we talked about. Like, for example, the dehydrogenation reaction. So M actually stands for monofunctional. It is dehydrogenation just monofunctional, and it just needs the platinum as an active site for doing the reaction. The dehydrocyclization needs both M and B. That means bifunctional, where it needs platinum as well as the acidic site. Isomerization is just the bifunctional, which is platinum and acidic side because it is actually it needs a little bit of hydrogen to accelerate the reaction. Hydrocracking again it is bifunctional where it needs both platinum and the acidic function promote this reaction. Similarly, hydrogenolysis is primarily the metal function part, which is actually being promoted by platinum. The disproportionation or alkylation again is by metal only because there's a hydrogen transfer reaction taking place here. And sorry, this is the transformation of the molecule. So this needs an acidic site, and the coking is of course needs both. It is promoted both by the platinum and the acidic site. So ultimately, the catalyst is actually a kind of a balance between the requirement of both the metal part and the acidic side. And this is the overall physical properties of this catalyst. It's pretty high surface area, 175 to 230 square meter per gram. Pore volume 0 0.5 to zero point 0.8 milliliter per gram, but pretty low bulk density. Actually, the trend is to actually increase the bulk density so that in the same reactor volume, you can put more catalyst so that you actually get higher conversions. We need, of course, good mechanical strength because actually a typical reactor could be something like 10 meters tall. And so the catalyst at the bottom sees the full head of the catalyst sitting above it. And so the bottom part of the catalyst should not get crushed to a powder. Otherwise, it will increase the pressure drop across the reactor. So mechanical strength and attrition index, these are the two very important variables in terms of the hardness of the catalyst. The shapes, there are two types of shapes that we produce. It is either spheres or extrudates. This is extrudate is like like the sivai that we produce. It's like the spaghetti. So this is so it's a long extrudate, which is roughly about 1.2 meter diameter, 1.2 millimeter diameter, maybe about 3 to 4 meter long. सिवई की खीर जैसे खाते हैं तो सिवई टाइप का ये पत्ता है. And but these extrudates is the shape which is preferred, either extrudate or trilobe. This is the shape which is preferred in a semi-regenerative catalytic technology. That means the semi-regenerative, reformers. While spheres is preferred in CCR. Why spheres is preferred in CCR? Because actually the catalyst, the continuous catalytic reformers, the catalyst actually moves, so it is easy to move a sphere rather than an extrude. And these spheres are again 1.6 to maximum 2 millimeter diameter. And it is this is of course platinum tin. So any extrudate would be platinum rhenium. Any sphere would be actually platinum tin. Kindly remember that. Finally, at the end of the discussion, as far as the catalyst is concerned, no discussion will be complete unless we talk about the reasons for deactivation of this catalyst. Of course, the reason is of course the coke deposit, which is inevitable, but we actually then regenerate the catalyst by burning off the coke. Or the poisons, okay, like if suppose our desulfurization or denitrification is not perfect in the step before, or the chlorine or the metals, actually they actually are the poison. And then over a period of time, because of the high temperatures that the catalyst sees, like 510, 520, 530 degrees Celsius, the crystalline structure of the gamma alumina gets what you call it gets shattered. So you get sintering or agglomeration, etc. So because of which actually this is a slow process. Of course, it takes roughly 4 to 5 years for this to actually start seeing some impact on the catalyst. Around 4 to 5 years, you are kind of ready to change the catalyst. We talked about the coke formation on the catalyst. It results from a series of reactions that happen because of polymerization and polycondensation. Of course, we saw that lower the temperature, less is the coking, and it is promoted by high temperature. And that's why we actually try to limit the endpoint of the feed. So the higher the endpoint, you actually start getting touring aromatics like naphthenes, etc. in the feed. That actually is bad news because touring aromatics will actually decompose to make coke. And so what does coke does? It's a temporary poison because it just reduces the active surface area. But then you actually burn off the coke again to regenerate the catalyst to its almost equal to the what is the fresh catalyst is. As far as the poisons are concerned, there are two types of poisons. One is called the temporary poison, those which can be removed from the catalyst without unit shutdown. If suppose there is more sulfur coming in, so if the catalyst deteriorates, if you start putting feed with a low sulfur, the activity and selectivity is restored. So basically, the same thing goes with sulfur, nitrogen, chlorine, and water. This is the tolerance limit. We try to actually maintain these less than 1 ppm. Of course, moisture, as I told you, it actually removes the chlorine from the support. So that is something that we need to look at. The permanent poisons are, of course, the heavy metals which might be there along with the feed. Of course, these are at ppb level, parts per billion level. But over a period of time, let's say in 5 years, 24 by 7 operation, they actually, there's quite a significant quantity of heavy metals which get deposited. And that actually also leads to a slow loss of activity. And this cannot be recovered. So actually, the catalyst needs replacement. So it's not only sintering and agglomeration, but also these heavy metals which are present in even if it is present in ppb level, parts per billion level, or part per trillion level, over a period of 5 years we do get significant quantity of these things, enough to actually uh, degenerate the catalyst. So finally, there are several companies in the world who actually supply this catalyst. Overall, there are two major leaders worldwide. So if you go to any of the 600 refineries that we have in the world, including the 23 refineries that we have in India, you will either find the reforming catalyst either from UOP or from Axens. UOP is a big licensor and a technology developing company in UOP in the US, in Chicago. They are headquartered in Chicago, next to in an outer suburb of Chicago called Des Plaines, DESPLAINE, very near to the Chicago International Airport. While Axens is actually the marketing arm of the French Institute of Petroleum called IFP. It is called Institut du French du Pétrole, and they have a big research center in Lyon, in France. And this is a big company again. Actually, IFP is more like government funded, the French government funded organization, although it has become quite independent now because they have been able to license and market a lot of their technologies and products worldwide. So, and in fact, India owes a lot to IFP, Institute du French du Petrol, because the previous organization where I worked at the Indian Institute of Petroleum, when actually the government was thinking about creating a research institute in the area of petroleum, the government of India and the government of France, they signed an agreement for IFP to actually design such an institute in India. And so Dehradun was actually identified as as a location. And IFP sent quite a few of their scientists, about 8 to 9 scientists came to India, and they lived in Dehradun from something like 1962 to 1966, almost 5 years. And they actually laid down the foundation of the Indian Institute of Petroleum at Dehradun. So, and as a former director of that institute, I feel, very, what I should say, obliged to an organization like IFP, who actually reached out to the government of India. I'm talking about IIP was established in 1960, 1960. And so from 1962 to 66, IFP scientists were there who actually laid down the structure. So, in fact, if you look at the IIP research laboratories and the research infrastructure, is very similar to IFP research structure in Lyon. In fact, in 2019, I had the opportunity to visit their research center for the first time, and I found that there was not much difference between what we had and what they had. Of course, they had developed much beyond what we could, but yeah, the overall blueprint remains the same. So that is all that you have that I had today.